How many numbers would you need to describe the moon? At first glance, the task seems manageable, but the complexity soon reveals itself to be overwhelming. The moon is pockmarked with a wide variety of craters, scars from billions of years of asteroid impacts. If we found an exomoon orbiting a similar exo-Earth in another solar system, even if it were superficially similar to ours, the pattern of its craters would be completely different. To characterize each precisely, at a minimum, we would need to provide two coordinates, latitude and longitude, for every one of the thousands of craters, along with data on its diameter, depth, and geological age. Very rapidly, we find ourselves needing thousands of numbers just for a basic topographic map. If we add the chemical composition of the surface, mineral variations in different regions, and internal structure, the numbers jump from thousands to millions. And the moon is one of the comparatively simpler objects in the cosmos. How many more numbers would it take to describe a living planet like Earth? A pulsing star? A nebula stretching across light years? Now, consider the most massive and extreme object in the entire universe. A black hole. The answer for these monsters might surprise you. 3. Just 3 numbers are sufficient to define a black hole completely. No matter how heavy they are, no matter where they were formed, and no matter whether they are in our own Milky Way or a billion light years away. According to the laws of modern physics, 3 parameters classify them absolutely: their mass, their electric charge, and their angular momentum spin. If you know these 3 numbers, you know everything there is to know about the black hole. But this creates a profound paradox. There are an infinite number of ways to form a black hole. It can arise from the collapse of a massive star, the merger of other black holes, or even the hypothetical compression of every encyclopedia and database of every civilization in history. How can all that information, knowledge, history, atomic complexity, be reduced to just 3 numbers? Where does the information go? Does the black hole forget its origins? Or does this information survive in some hidden form? To understand this, we must go back in time, even before Einstein, to the birth of a dark idea. In the 1780s, the life of a country priest in the Church of England was not exactly demanding. With a large house, a decent income, and curates to do the heavy lifting, there was plenty of time for leisure. But for John Michell, that time was spent thinking deeply about how the world worked. Michell lived under the intellectual shadow of Isaac Newton. A century earlier, Newton had shocked the world with the theory of universal gravitation. Anything with mass attracts everything else with mass. Nothing could avoid this force, not even, Michell mused, light itself. At the time, Newton argued that light consisted of tiny particles, corpuscles. If light was a particle and gravity was universal, Michell reasoned that gravity should pull light back. He knew the speed of light, measured accurately by James Bradley through stellar aberration, about 300,000 kilometers per second. He also understood the concept of escape velocity, the minimal speed an object needs to overcome a body's gravity and never return. For the moon, it is 2.4 kilometers per second. For the Earth, 11.2 kilometers per second. For the Sun, roughly 617 kilometers per second. Michell then proposed a thought experiment. What about a body so dense and massive that its escape velocity exceeded the speed of light? In that case, light emitted from the surface would be tugged back before it could escape. The object would be invisible to the rest of the universe. It would be a dark star, although Michell used Newtonian physics, which would later be replaced by Einstein. He had described the fundamental concept of a black hole almost 2 centuries before the name was coined. His work, however, was filed away as a mathematical curiosity for 150 years. The next chapter of this story would not be written in a quiet office, but in the chaos of the trenches of World War I. While serving in the German army in 1915, astronomer Karl Schwarzschild found intellectual refuge in the equations of Albert Einstein's brand new general theory of relativity. Einstein had proposed that gravity was not a magical force of distance, but the curvature of the fabric of space-time itself. Einstein's equations were, and are, formidable. Schwarzschild decided to look for the simplest possible solution. What happens to space-time around a perfectly spherical, static mass? He found what we now call the Schwarzschild solution. In it, he discovered a critical radius. if you compress a mass below this radius, called the Schwarzschild radius, something bizarre happened in the math. Certain terms went to infinity. This indicated the presence of an event horizon. Imagine a spherical shell around the mass. Outside of it, like an escape. Inside, space-time is so curved that all paths lead inward. For an astronaut crossing this line, space and time swap roles. The center of the black hole is no longer a place, but an inevitable moment in their future. Below this boundary lies a singularity, a point where density is infinite and the laws of classical physics simply stop working. For our sun to become a black hole, it would need to be compressed into a 3-kilometer sphere. The Earth would need to be the size of a marble. For decades, physicists like Richard Feynman dismissed these studies, considering general relativity a backwater with no practical experiments. Everything changed in the 1960s. The resurgence of gravity as a cutting-edge science is inextricably linked to Stephen Hawking. Diagnosed with ALS at age 21 and given a life expectancy of only 18 months, Hawking channeled his vital urgency into research. In collaboration with mathematician Roger Penrose, Hawking proved that black holes and singularities were not just mathematical anomalies, but inevitable consequences of relativity if enough matter was concentrated. They created Penrose diagrams, visual tools that allow us to map the causal structure of the universe. What can influence what? At the same time, X-ray astronomy began observing the sky above the clouds. In 1971, Cygnus X-1 was discovered, an X-ray source so intense and compact that it could only be one thing, a black hole devouring a companion star. What was theory became physical reality. It was during this period that the famous phrase emerged, "Black holes have no hair." This means that, unlike a human being who has hair, wrinkles, and scars that tell their story, a black hole discards all its complex characteristics. All the information about what fell into it is erased, leaving only mass, charge, and spin. But this created a profound problem for science, the second law of thermodynamics. The second law of thermodynamics is sacred. It states that entropy, a measure of disorder or the number of internal states of a system, must always increase. Imagine physicist John Wheeler talking to his student Jacob Bekenstein. Wheeler proposed a dilemma. If I mix hot tea with cold tea, entropy increases, disorder increases. But if I throw that cup of tea into a black hole, all that entropy disappears from the visible universe. Cleaning up the crime against the second law, would the black hole be an entropy sink? Bekenstein challenged this. He proposed that the black hole must have entropy. Furthermore, the entropy of a black hole does not depend on its volume, but on the surface area of its event horizon. Every time you throw something inside, the area of the black hole increases, ensuring that the total entropy of the universe never decreases. Stephen Hawking was initially skeptical. If a black hole has entropy, it must have a temperature, and if it has a temperature, it must emit radiation. But by definition, nothing escapes a black hole. While trying to prove Bekenstein wrong, Hawking discovered something that would change physics forever. Using quantum mechanics to analyze the empty space at the edge of the event horizon, he realized that the vacuum is not empty. It is filled with virtual particles that constantly pop in and out of existence. Near the event horizon, sometimes one of these particles falls into a black hole while the other escapes. To the outside universe, it appears as if the black hole is emitting particles. This is Hawking radiation. The conclusion was shocking. 1. Black holes are not totally black. They glow faintly. 2. They have temperature. And contrary to intuition, the smaller the black hole, the hotter it is. A black hole with the mass of a mountain will be incredibly hot, while one with a mass of 1 billion suns is almost as cold as absolute zero. 3. They evaporate. By emitting radiation, the black hole loses mass. Eventually, it vanishes in a final explosion of energy. This brings us back to the initial paradox. If a black hole evaporates and disappears, and all that remains is random thermal radiation, what happened to the information of all the things that fell into it? Where are the data from the encyclopedias, the stars, and the stories it consumed? The discovery that black holes have entropy and temperature united 3 branches of physics that previously didn't speak to each other. General relativity, the very large, quantum mechanics, the very small, and thermodynamics, heat and energy. Today, black holes are seen as nature's ultimate laboratories. They suggest that the universe may function like a hologram, where all the information of a 3D volume is actually encoded on its 2D surface, exactly like the entropy of a black hole is on its surface, not its interior. What started as a curiosity by an English priest in the 18th century became the key to understanding the very structure of reality. Black holes are not just tombs of stars. They are the guardians of the deepest secrets about how information is preserved in the fabric of the cosmos. If you made it this far, it's because the complexity of the universe fascinates you as much as it does us. If you want to continue exploring the mysteries of space-time and the frontiers of science, subscribe to the channel and hit the notification bell. We post documentaries like this every week. What do you think happens to the information that falls into a black hole? Is it destroyed forever, or is it stored on the event horizon like a hologram? Leave your theory in the comments below. If this video expanded your mind, share it with that friend who also loses sleep thinking about the scale of the universe. See you at the next horizon. Until then,